There you are.
Yeah, we getting a little problem over here with my stuff. It's not stable for some reason right now. But that's why we wanted to meet at 4 to make sure all these bugs are taken care of.
No, that's fine.
Yep. So I could hear you well. Let me go ahead and give you the ability now to share your slides, your PowerPoint. So you should be able to share your screen right now. So again, welcome to everyone online to our 11th seminar in the Andrews University Department of Chemistry and Biochemistry seminar series. And we'll be hearing a very important, I think, lecture today. Hopefully some of my high school kids are listening, and I even sent this out to the general public as well, because I think it has importance for and relevance for everyone. Before I get in too far, however, our student will, one of our students will introduce our speaker. Our student's name is Theo. I'm not going to try to pronounce his last name. I will mess it up. Theo is born in Indonesia, but spent most of his life in Singapore. He went to high school um, also in Singapore, I assume here. And his major with us is biochemistry, pre-med. Career goals include being an anesthesiologist. And something fun about Theo is that he had a seasonal pass for Universal Studios in Singapore. And for some time, using this seasonal pass, he used to go to the Universal Studios like even like 3 times a week. He was a frequent visitor there. I've never been to a Universal Studios, so you've got that on me and maybe many others. Um, I'm thinking that you probably had a really good time, hence the reason for going back 3 times a week. Anyway, Theo, you could go ahead and introduce our speaker.
Professor Emeritus Joseph Oliver Falkinham III received his bachelor's in bacteriology and PhD in microbiology from the University of California, Berkeley. Dr. Falkinham served in the U.S. Air Force from 1969 through 1972, directing hospital clinical laboratories. Following a postdoctoral fellowship in the laboratory of Roy Curtis at the University of Alabama Medical Center, Dr. Falkinham joined the Department of Biological Sciences at Virginia Tech in 1974. His most recent research is focused on mycobacteria, Legionella, and amoeba in household plumbing, biofilm formation by mycobacteria, isolation and identification of new antimycobacterial antibiotics, and mechanism of action of antibiotic dendritic amphiphils. He authored and co-authored 3 books, 31 book chapters, 25 invited review articles for scientific journals, and published 136 peer-reviewed papers in journals. He has presented multiple invited papers and lectures on mycobacteria at national and international meetings and is considered an international authority. He has mentored 19 master's degree and 7 PhD students and served on multiple graduate advisory committees in the Department of Biological Sciences and other departments. He has served on 3 different professional editorial boards and was editor for the International Journal of Microbiology. In 2015, he became a fellow in the Royal Society of Public Health London and received the Gardner Middlebrook Award in 2003 for mycobacteriology by the American Society of Microbiology. In today's lecture, he He will be talking to us about premise plumbing and waterborne pathogens. So join me in welcoming Dr. Falkinham.
Thank you, Theo. I appreciate that invitation very much. And you remind me of my grandson, Jack, who was an undergraduate chemistry major at the University of Oklahoma. And he's now in his second year of residency in obstetrics and gynecology in Oklahoma City. So you're trotting a known path, and I wish you success. And I'm very jealous of the fact that you were able to go to Universal Studios. I love Disney. Whenever I can, my family and I, we all just run down to Disney and spend 2 or 3 days. So I'm delighted to do this. Desmond, Dr. Murray, I'm delighted to do this. This is a clever way of having seminar speakers from a distance, and I'm looking forward to it today. I'm going to talk about premise plumbing and waterborne pathogens. Premise plumbing, and we'll go to the first slide, is a carrier of waterborne pathogens. And the frequency of these infections has been increasing at rates between 5 and 10% annually for different bacteria. Some of the reasons for this is that the US population is getting older, and older individuals are more susceptible to these infections. Many of these infections are pulmonary infections. So they get diseases that look like pneumonia or tuberculosis. We also have people that are immune deficient. They're immune deficient due to cancer or cancer chemotherapy, both of which reduce your immune resistance, and you're more susceptible to infection. Finally, we also have immune deficiency due to HIV infection. HIV infection results in the loss of T cells, and the patients are much more sensitive to infection. So these infections that we see in the US population, as well as in Europe, Japan, Australia, are increasing in frequency, and their infections have been linked to the organisms in premise plumbing. So what is premise plumbing? You and I, all of us here today, are surrounded by premise plumbing. These are the pipes, the plumbing in houses, apartments and condominiums, hospitals, long-term healthcare facilities, hotels, and I should have added this, dormitories as well, thinking about universities. So that plumbing is the deliverer of these organisms. Now, what are the characteristics of plumbing that make it so amenable to these microorganisms? First of all, the pipes are relatively small, and so there's a high surface to volume ratio, meaning that there's a lot of surface area for these organisms to colonize and stick to. Plumbing is composed of a variety of different materials and surfaces. You may have plastic pipe in your home or apartment or condominium. You may have copper pipe. You may have galvanized pipe, which is zinc coated. You may have stainless steel. So the organisms can choose the surface with which they want to react. Very often in premise plumbing, the water is recirculated. That means that the water is continually moving through the system. This is particularly the case in hospitals, large office buildings, condominiums, and apartment houses, where they have a central heating system, and rather than give you a long delay before you get hot water, the hot water is circulated regularly. That means the organisms are in relatively warm water all the time, and water, of course, and temperature regulates their growth. Warm water they grow more. There's periodic heating and cooling. The heating not enough to kill off the organisms, the cooling not enough to kill off microorganisms. There's also periodic stagnation. When you left your apartment or I left our home this morning, after I had my shower, I turned the water off. Well, the water had been flowing, the pipes were all nice and warmed up, and I left them that way. And over a period of time, the amount of disinfectant in the water falls, the amount of oxygen falls, but the organisms that are in our drinking water are perfectly happy and have adapted to those conditions. Now, finally, drinking water, which for the most part we're talking about here, has a low organic matter content. So the organisms that we see in premise plumbing are adapted to living in an environment where there's low organic matter. Most of them are common in water that we use as a source of drinking water, rivers, lakes, and streams. Now, there's a good deal of chemistry involved with premise plumbing, and it has to do with their interaction with microorganisms. Pipe materials. I said before that we had a variety of pipe materials in premise plumbing. Well, we have copper. There are lots and lots of copper pipes, copper valves, copper joints in premise plumbing. Copper is an interesting metal because it's both required by mostly all microorganisms, but at high concentrations, it is inhibitory. I'll talk about a couple of organisms that don't like copper at all. It's an organism, Pseudomonas aeruginosa, which is a waterborne pathogen, and it is relatively sensitive to copper. The second one on the list there is iron. Iron is required by all microorganisms. They go to great lengths to get iron from the environment. They make many metal binding compounds that bind metal and bring it into the cells because iron is required by mostly all the OPP, all of these opportunistic premise plumbing pathogens. Now, I would point out that we found a very interesting situation in Flint, Michigan, when my colleagues from Civil and Environmental Engineering at Virginia Tech went up there when there was an outbreak of lead poisoning. The year before there was an outbreak of lead poisoning, there was a 10-fold increase in the number of Legionella Pneumophila infections, Legionnaire's disease, in the Flint, Michigan area. Now, as you may know, the regulatory people having to do with the water system in Flint, to save money, didn't add anti-corrosion chemicals, phosphates, and unfortunately, they got the release of some of the corrosion products, and iron is prevalent in those corrosion products. And so iron was released in the Flint water, and that iron stimulated the growth and the numbers of Legionella Pneumophila. So there was an outbreak, it was tenfold. It went from about 8 to 9 cases annually to 80 cases annually in that year before the Flint outbreak. My students, in working with the mycobacteria, discovered that zinc stimulates mycobacterial numbers. In fact, if you look at the concentration of zinc in natural waters, you find that the concentration of zinc is correlated with the number of mycobacteria. Pipe materials and the metals also interact with disinfectant. Now, disinfectant, primarily chlorine here in the United States, is added to water during its treatment in the big plants and then sent out through all the pipes. And what we have in our homes is the rest is what is left after that transport through the pipes. it's usually enough to kill off fecal pathogens like E. coli and Salmonella and Shigella that cause diarrheal diseases. Unfortunately, pipe materials can reduce the concentration of disinfectant, and mostly all of the organisms I'm going to talk about are relatively resistant to those low concentrations that we have in our homes. Corrosion does two things. First of all, it traps metals so that when corrosion products are released, the metals, the iron in particular, is available, but also the corrosion provides more habitats, literally rough surfaces with nooks and crannies for these microorganisms to live, grow, and persist. Because a water system, whether it's a distribution system for a town or county, or a plumbing system in your home, or a hospital, is a flowing system, just like a river. And these organisms have adapted to a flowing habitat because they bind to surfaces and form what we call biofilms, which are mixes of cells and extracellular material. I mentioned before the loss of corrosion control in Flint. Not only did we get the release of lead, which the young children were drinking, but also we got the release of iron, which led to increased numbers of Legionella. Now, here is one of microbiologists' favorite things, a list of microorganisms. The organism that my lab studies are the first ones listed: Mycobacterium avium and Mycobacterium abscessus. A very common one is Pseudomonas aeruginosa, responsible for lots and lots of swimming-associated ear infections. A relative of Pseudomonas aeruginosa, Stenotrophomonas multifila. Another relative, Acinetobacter baumannii. Actually, the name Baumannii is the last name of a fellow I knew as a graduate student at Berkeley, a fine microbiologist, Paul Baumann, who is now at the University of California, Davis. And he studied, and as a result of his studies, this particular species was named after him. Another organism is Sphingomonas paucimobilis. Paucimobilis, that species name means slow moving. An organism that we have recently started looking at very closely are called Methylobacterium. And you can actually see Methylobacterium in your home, or particularly in the bathroom, where in the shower you'll see pink, salmon pink color, which is due to the growth of these Methylobacteria. They are relatively harmless microorganisms, but what we discovered, and this was from work done by others, that when the Methylobacteria are present in your shower, you don't have Mycobacteria. And if you have Mycobacteria, you don't have Methylobacteria. These seem to compete for binding to surfaces, pipe surfaces and bathroom surfaces in our homes. The organism Cupri avidus. Cupri refers to copper. Avidus requires it binding. It has an absolute requirement for copper, is very tolerant of copper, and it too is one of these organisms that's in our premise plumbing. The last on the list there is probably the most famous, Legionella pneumophila, first discovered in 1976 due to an outbreak of pneumonia amongst veterans of the United States military who were attending a Legionnaires convention in Philadelphia. A substantial proportion of the people, of these men, came home with a pneumonia. The pneumonia did not respond to antibiotic therapy as did typical pneumonias. It took a while, but ultimately Legionella pneumophila was found to be a brand new agent. It still causes diseases now associated with premise plumbing. Now, these organisms on that list all have a number of shared characteristics that make their residence in our household plumbing likely. The organisms are relatively impermeable. Now, that's one of these yin and yang characteristics. Impermeability means that nutrients don't get in very well. But impermeability also means that antibiotics and disinfectants can't get in very well. So these little cells are able to grow in the presence of disinfectants. Because they're impermeable, they grow slowly because they can't take in nutrient very well. They all form biofilms. They adhere to surfaces, usually through hydrophobic interactions. They don't want to be in water and interact with charged hydrogen and oxygen. They would rather stick on surfaces. Sticking on surfaces protects them from that ionic environment of water, but it also prevents them from being washed out. As the biofilm grows and becomes thick, and it can have hundreds of thousands of cells in a relatively thick, gooey, slimy layer, that layer protects the cells from disinfectants as well. They just don't penetrate. These organisms grow at low organic carbon levels. Although we grow them in the laboratory in rich media, they're perfectly happy growing in some cases, water with very little organic matter. They're desiccation resistant. If they stick on surfaces and that surface gets dry because of an intermittent water flow, they're perfectly happy living in the biofilm. The biofilm, by the way, is about 80 to 90% water. It is mostly water with all of these polymer materials. They grow under reduced oxygen concentrations, which would be under conditions of stagnation. So when the water stops flowing and it gets stagnated, these organisms keep growing. They're somewhat temperature resistant. And that means they can grow in a water heater. And in studies we've done in Philadelphia, in a suburb of Philadelphia, it appears that the major site where these organisms can grow once they get in your house is that water heater. They are readily aerosolized. In other words, they are transferred in droplets from water to air. And finally, a common feature of these organisms is that they grow in free-living amoeba and in protozoa. Normally, amoeba and protozoa graze in the biofilms on pipe surfaces. That's one of the places where they grow, one of their habitats. However, when they eat, phagocytize one of these organisms that were on that previous list, the organisms, rather than being killed and used for nutrient, use the amoeba or protozoan as a host. It protects them from the outside, and in a number of cases, ultimately, the organisms grow within the amoeba, and they can actually break the amoeba open, releasing many more cells. So it seems to be a kind of a life cycle for them. Now, one of the nice things that we do in the world is monitor water quality. Microbial water quality is to avoid contamination of water from fecal pathogens. The indicator, the organism we use is Escherichia coli, which is it's in every mammalian GI tract. And so it's present in fecal material. So E. coli numbers are monitored in drinking water all the time in every drinking water system across the United States. That also includes swimming pools, hot tubs, everything in which the public has an access to. But E. coli is not a normal inhabitant of drinking water. The organisms I listed before are normal inhabitants. Escherichia coli is a contaminant. So if E. coli is absent, that doesn't mean there are none of these premise plumbing pathogens. So we have a challenge to the drinking water industry now, and that is, how are we going to monitor these to help people out? Now, I mentioned biofilms, and I wanted to have a brief presentation here about biofilms because they're a key element in the colonization of our homes with these organisms. A biofilm is a surface adherent cells within an extracellular matrix. You can refer to the extracellular matrix as a slime. Depending upon the organisms that are making up the biofilm, it could contain polysaccharide, long-chain sugar molecules, lipids, long-chain molecules, proteins that are made by cells and then exported out of cells, and DNA. All of these molecules here are long-chain molecules, so they're very viscous, and they allow the microorganisms to stay stuck to these surfaces. That matrix also provides an impermeable barrier to the entrance of nutrients, of oxygen, disinfectants, and antibiotics. So it's protective, but it does limit the growth rate of these organisms because nutrients and oxygen can't get in. But they have the benefit of not being inactivated by disinfectants or antibiotics. By the way, I would also point out that biofilms are also formed in human tissue. Patients with pneumonias or tuberculosis have a biofilm made up of those organisms. Now, what are the consequences of biofilm formation? And I would like to point out that microorganisms survive because they find a way of doing one thing that allows them to survive and put their baby cells in the next generation. Biofilm formation means the cell can reside in the habitat it is and persist. It doesn't get washed out. That also means in a drinking water system, the cells in those biofilms are resistant to desiccation. The cells are resistant to disinfection as well. Disinfection because the disinfectant can't penetrate. Desiccation because the biofilm provides those cells with enough water for them to. Now, what that means is that even if you drain a water reservoir, a hot tub, a shower head of water, the cells in the biofilm are still alive. And as soon as water comes in, the water can pick up some of those cells. And so literally those cells inoculate the water that have survived disinfection, desiccation, or sitting for just a long period of time. So what are the sources of these? How can you get infected? Well, you can drink water, premise drinking water, just the water in your house. If you suffer from gastric reflux, in which some of the stomach liquid moves up your throat, up to your throat, that can be aerosolized and those organisms transferred into the lungs. You can get aerosols. When you turn on a water tap, you're making an aerosol. If you take a flashlight in the dark, turn a water tap on and shine the light through the water or above the sink, you'll see aerosols. It took me a while, but some fine work done at the University of Virginia Medical School, where they had an outbreak of one of the organisms on that list. It took me a while to realize that drains are also sources of these microorganisms. And so when the tap flows water directly into the drain, you get an aerosol from the drain. And that's how some of these organisms can be released. Through the activity of a young man who was worried about infections in his mother and father, he sent me a sample of drinking water from a refrigerator tap. Now, it's kind of a unique, highly developed US society that we have refrigerators with drinking water taps in the front of them and ice dispensers. Well, those turn out to be rich sources of these organisms. The drinking water and the ice have high numbers of these organisms. We and a number of other people have shown that aerosols from showers and hot tubs. So when you go into a bathroom after a shower, there's a mist. We don't call it a mist. We have a sciencey term of aerosols, small droplets. Those droplets are droplets from the water and contain high numbers of these waterborne pathogens. The same is true of hot tubs. We also found that humidifiers, depending upon the type of humidifier, can generate a very rich aerosol containing these microorganisms. Air conditioning systems in homes work by water soaking a filter and then air blowing through it. And warm air blowing through a water-laden filter, the air is cooled, and so you have air conditioning. Well, you also are picking up the organisms that are in the drinking water and now are transferred to the air. Now, these waterborne pathogens are not just from water. They may originate actually in soils and are carried into bodies of water, surface water like lakes and streams and rivers by water flowing. And we found that dusts from soils, especially potting soils that you buy in bags, are rich in these pathogens. And so if you're at risk for one of these infections, then you need to wear a mask, something we've all become very familiar with in the last year, but you can wear a dust mask to prevent inhaling dust with these organisms. So the routes of transmission from particularly in premise plumbing, but also just around the house, swallowing tap water, adding ice from a refrigerator to drinks and then drinking it. You get aerosols from showers and hot tubs. And the aerosols can stay in the room and be transferred to other rooms so that a whole home can be filled with aerosols from a shower, aerosols from humidifiers. During the winter here in the east, the air gets very dry. People like to humidify the air, but there are certain humidifiers, namely those called ultrasonic humidifiers, that generate very dense aerosols of these premise plumbing pathogens. And of course, as I mentioned a minute ago, aerosols from gardening dusts cause problems. So what can you do? These are the questions we get from hospitals after an outbreak of infections. Well, one way to do it is to circulate very hot water, 70 degrees centigrade, higher than I think most water heaters can get, so it's superheated water. If you circulate that through, that high temperature kills microorganisms. Another way of doing it is to circulate very high chlorine levels. Normal chlorine level is 1 part per million. You can circulate chlorine at 5 parts per million. Now, both of those have hazards. You literally have to close off the entire system to use either one of those, and then make sure you rinse, flush the water to get rid of the chlorine, or allow cold water to equilibrate with the hot water to avoid scalding. So those are our last sort of resort items, but they have been done by any number of hospitals, hotels, and long-term care facilities when they've had outbreaks of these infections. However, The problem is, even with both of those treatments, biofilm removal is very difficult. What we discovered, and this is work that was earlier done back in 2000, detergents. Now, detergents break hydrophobic bonds. That's why they're so good in removing stains and dirt and protein and other things from our clothes. They break those bonds and allow their release and being carried off. Well, they also make biofilms very porous, actually resulting in the release of microorganisms, but they increase the penetration of disinfectants. So an enzyme detergent combination with a disinfectant like chlorine will kill many, many organisms in biofilms. Finally, and this is a plug for Virginia Tech and one of my colleagues, I'm working with a colleague who is developing antimicrobial surfaces. Now, you all know there are surfaces all over the place. And so he has developed surfaces that are antimicrobial. When microorganisms come in contact, they are rapidly killed. So we could use those surfaces on pipes in homes. Here's a list of things. I'm almost nearing the end of this. Things that people can do in their homes as a remediation measure. Now, I would point out that a small proportion of people are susceptible to these infections. People with pre-existing lung damage, immune compromised people, people undergoing cancer chemotherapy, hard drinking, hard smoking World War II veterans, and veterans of Vietnam. So if you're in one of those categories, you might want to reduce your exposure to these organisms. Well, what can you do? You can drain the water heater because these organisms grow in the sediment that collects in water heaters. You can raise the water heater temperature to 70 degrees centigrade. On a regular basis, you could keep the water heater at 55 degrees centigrade. That's 130 degrees. But whenever I say that, people remind me that I would increase the risk of scalding. You have to be very careful. You need to flush your pipes. In the parlance of the civil engineers, you want to reduce the water age and prevent portions becoming stagnant. I realized after we did one of our very first studies of mycobacteria in premise plumbing across the United States, some of the patients who were collaborating with us had second homes. Typically, they would be the people who, during the winter, went down to Florida or South Carolina or out to Phoenix, Arizona to get warm. Well, while they're not in their second home, the microorganisms are having a ball and growing to very high numbers. So the important thing is, if you go to a second home, turn the water on and let it run for about 10 minutes. Drain the water heater immediately because your home has become a microbial culture facility. If you can, you want to make sure you don't have dead ends in plumbing in houses. Dead ends serve as places where microorganisms can collect and recolonize the water. There are filters. The filters are very small. Their pore size is 0.22 micrometers in diameter, but those can be put on taps, and there are even shower heads with those filters, and they prevent microorganisms, all microorganisms, from going through. They don't prevent viruses from going through because they're much smaller. You can unscrew your shower head, excuse me, put it in a bucket with Clorox and submerge it for 30 minutes. That long dose of course being the combination, the multiple of concentration and duration of exposure, that will kill all these organisms. You can remove aerosol generators. Many homes have little add-on things on water taps that make a nice smooth flow. Well, they make aerators, they make aerosols as well. And now this is becoming the case in the United Kingdom. In England, they're changing the taps in sinks so that the tap doesn't drain directly into the sink, but they flow into the sink to reduce the aerosols. Now, you may all be aware of the talk about climate change and developing green buildings. Green buildings would use less energy to reduce global warming. Well, my colleagues in civil engineering and I have considered green buildings, and we're a little bit concerned. For example, green buildings have lower water heater temperatures. For the most part, they're heated by solar heating. There's a longer water age and residence time in the home, so microorganisms can grow longer to higher numbers. There's reduced flow. You use misting shower heads to reduce water flow, and you get an increased biofilm buildup, which suggests to us that green buildings will result in increases in infections caused by these organisms. Alternate disinfectants have also been suggested. Monochloramine is an ammonia-made derivative of chlorine that penetrates biofilms better. The problem is that mycobacteria, the organisms my lab studies, are very resistant to monochloramine, and in one, I think now 2 cases, when a water system changed from chlorine to monochloramine, they discovered that Legionella disappeared with monochloramine, but the numbers of mycobacteria rose. So what kind of challenges do we have here in drinking water with these organisms? An aging population needs increasing proportion of people at higher infection risk. The increased availability of chemotherapy for cancer treatment and reduced immune protection that goes in hand puts more people at risk. And in the absence of monitoring, because we don't have a way of monitoring these organisms right now, how do we protect those at risk? So I'll close with that slide. I invite lots and lots of questions. I'm going to go back now, pardon going back through all the slides. I'm going to go back to my first slide because at the bottom of that is my email at Virginia Tech, JOFIII. As Theo said, I am Joseph Oliver Falkinham III. I'm at Virginia Tech, so it's part of the EDU system. If anything has come up and you want to ask a question, I'll be more than happy to answer it by email. And if we have some time now before everyone has to go back to lab or back home, and I'll let Dr. Murray monitor any questions at all, and I'm happy to ask. And again, I want to give you my sincere thanks for the opportunity of giving this brief talk. Thanks very much.
Thank you. Thank you very much. Okay. Do you guys have questions? You could put the questions in the chat, or looks like we're getting a few here. So Aaron, you could unmute yourself and ask.
Yeah, so can you hear me?
Yes.
All right.
I can.
Okay, good. So I was just thinking about you mentioning aerosolization of these microorganisms in drains. So would they possibly be taken care of by like a routine use of a drain cleaner? Because typically drain cleaners are for food and those kind of particulates. But if you're using like sodium hydroxide or sulfuric acid, that's pretty strong. Would that kill those bacteria? And if you used it regularly, could it prevent them from being aerosolized because they aren't even there?
Yeah, it's a very thoughtful question. Thank you. Yes, because most of the drain cleaners are alkali based, either lye or sodium hydroxide, that will kill off all these organisms. And by removing the material in the drain, they will also reduce the habitats for these microorganisms. So that would be a very good thing to do on a regular basis. I don't actually have that on my list of suggested measures that people can take. And with your permission, I'd like to add that, please.
Absolutely.
Thank you.
Very, very good, very good. It looks like John Juan had a question as well. You could unmute yourself and ask a question. John Juan? Okay, if he doesn't have a question, what's the current status of monitoring? Because you talked about that a couple of times, mentioning that we don't really have. Do you know of research, however, that's ongoing to try to develop monitoring systems for these premise plumbing pathogens?
Monochloramine has come to the fore because chlorine is so reactive that we get carcinogens produced by chlorine interacting with organic matter in drinking water.
Mm-hmm.
And so in order to reduce the levels of those, which are actually measured nowadays, people have considered using monochloramine. But like everything in the drinking water field, and undoubtedly everywhere else, you have to make sure that when you do something for one good reason, that you're not creating another problem. And the problem that concerns me now is that monochloramine seems to support the persistence of some of these waterborne pathogens. It's good at killing off Legionella, but it's very bad at killing off Mycobacteria and perhaps others. So we are sort of waving flags on the sideline to make sure that we get a chance to look at all these ramifications of substituting things to make sure that we're not creating a worse hazard.
Okay, very good. Loris, you could unmute yourself and ask your question. You have a very important question. No?
Yeah, my question was, what is currently being done to inform property owners about this danger? Because this is my first time hearing about this.
What are we doing to inform homeowners?
Yeah, homeowners, yes.
Primarily, the people that we inform are those that have risk factors.
I see.
So I work with the foundation that's down in Coral Gables, Florida, that is where people with mycobacterial lung disease work.
Mhm.
And they circulate my list of recommendations. I've also sent that list of recommendations to the Cystic Fibrosis Foundation because they get Pseudomonas infections, Pseudomonas being on our list. They get mycobacterial infections on our list, Acinetobacter infections that are on our list. And those individuals who have a defect in lung transport are very susceptible to infections caused by those organisms. They get a pneumonia. So we have told those people that they need to consider these measures in their homes. And because cystic fibrosis is an inherited disease, for those of you who've taken genetics, it's an autosomal recessive disease, that it appears in childhood, usually presents in a child with repeated pneumonias that are kind of inexplicable. And the diagnosis is relatively straightforward nowadays. The sweat, the perspiration of a child with cystic fibrosis is very salty, and which is part of the defect of transport. But those are children, and so the parents need to take measures so that the children can avoid some of the things that would lead them to, for example, inhaling aerosols of mycobacteria, inhaling aerosols of Pseudomonas aeruginosa.
So my follow-up comment then would be with the current situation that we're in with COVID-19 and the long effects after long COVID. What can you comment on that?
Well, I'm not a COVID person, but I do know about the human lung a bit, and
Yeah.
what worries me is that we've seen people with COVID, very bad disease. Fortunately, they survive. And what I'm worried about are long-term consequences of COVID infection.
Mm-hmm.
And I think that's basically where your question comes from. And you're very thoughtful in thinking about long-term consequences rather than short-term consequences. We need to keep COVID. We need to keep the fact that we're going to be facing all kinds of novel viruses that move through the world now with the speed of light, I think. We need to be considering those in the long term so that we are prepared. And when somebody presents with particularly one of these waterborne pathogen infections 10 and 20 years from now, that one of the first questions that their primary care physician asks is, did you have COVID or not? And that's going to be a very important question probably to ask everybody who comes in with a chest infection in the future.
Yeah, and I was just thinking in relation to this premise plumbing and how it affects the lungs, and then if you've had COVID, how will that impact you as well?
It will influence it a great deal.
Okay.
And that's the challenge now to the water industry. We need to develop ways of monitoring and then disinfecting water so we keep these numbers to a low, to really keep these numbers low.
Mm-hmm.
Thank you.
You're welcome. Thank you.
Very good questions. Very good question. John, did you want to go ahead and ask a question? Unmute yourself and ask a question.
Oh, yes. My question was that specific metals promote microorganism growth, or it inhibits it. Do you know anything about arsenic in relation to it? Is arsenic just toxic to all microorganisms?
Arsenic?
Yes.
Arsenic is an interesting, because it's the arsenate, which is a structural analog of phosphate.
Mm-hmm.
So most all organisms are sensitive to arsenic because it substitutes for phosphate. And so most organisms need the phosphate for synthesis of high energy phosphate. So they end up with real problems. So there has been some thought to using arsenic in a bound, maybe nanomaterial formulation to kill organisms. But those are things that are just being considered now. But yeah, some of the heavy metals might be quite useful in dealing with these situations and developing antimicrobial surfaces.
Mm-hmm. Mm-hmm. Okay, very good.
Thank you for the answer.
You're welcome. Thanks for the question.
Nicholas, you have a question? You could unmute, Nicholas. Nick? Okay, so I'll read the question for you then. So Nicholas had a question, does silver work for water purification? You might have said something not having the best, oh, okay, he's not having a good signal right now. So he wants to find out about silver and water purification.
Silver, along with zinc and copper, are leading, excuse me, are leading the charge to develop antimicrobial surfaces. The question is, how do you make those surfaces? How do you make them amenable to regular use? Are you going to coat something? For example, my colleague in chemical engineering who's developing an antimicrobial surfaces, you can coat doorknobs with copper, and then the doorknob, rather than being silver, shiny, brassy, or something like that, kind of has a rusty look to it, but it's antimicrobial. And so silver has been known as an antimicrobial agent. It's a good one because it's not used necessarily by microorganisms, unlike copper, which has uses in as a cofactor of various proteins, zinc in the same way. So those are leading candidates, and the challenge is to formulate them in such a way that they can be used usefully on surfaces and stable enough to stay on the surfaces for a longer period of time. So they're not just going to be wiped on the surface and be there for a short time, but you can leave them on for a long period of time. And that would avoid using disinfectants all the time. It would lower costs, which would be made up by the cost of the material, but you wouldn't have people going around wiping every surface every minute. And I see that in the grocery stores. I see that in the hospitals. Everybody's wiping surfaces.
So what about, as a follow-up in terms of the surfaces, what about quaternary ammonium type compounds that are found in some of these detergents and disinfectants to try to create antimicrobial surfaces? Do you know of anyone who is working in that area?
Yes, there are a number of products that have been used. One made under the trade name Microban. It's a company that makes treatments for surfaces. And the problem with the quaternary ammonium compounds is they're not as particularly strong antimicrobial agents as you would like. And so you want to get something that's going to be totally bound to things.
Okay, okay. All right.
Now, thinking of surfaces, yesterday I stopped off on my way between home and the university, stopped by a little place to get a cup of coffee and some scones that I really like.
Okay.
And when I paid, there was a little computer screen about the size of a paperback book or an electronic reader. And I used my finger to sign my name.
Right, right.
And we are surrounded by touch screens.
Yep.
If you go to a hospital now, you see touch screens being used all the time. We need to have coatings on those touch screens that are antimicrobial.
That's right. That's right. Yep.
So for your students, Professor Murray, who are entrepreneurial,
that's right.
That's where they need to start thinking and working.
Yep,
because COVID is not going away, influenza is not going away. These other microorganisms are not going to go away.
that's correct. That's correct. Isabella?
Yes, I have a question. So for the antimicrobial surfaces,
We're not hearing you too well, Isabella. You're breaking up. Do you want to write?
so if there's no contact with pathogens, if everything has an antimicrobial surface, how will children be able to, I guess?
You're breaking up. We're not hearing you. Isabella?
Isabella, are you worried? You mentioned children. Are you worried about children being exposed to low numbers and developing immunity, or actually picking up some of the microorganisms that surround us that are useful for them?
Correct.
That's,
Yeah.
Okay. Thank you. That's an awfully good idea. We can go overboard clearly with antimicrobial surfaces. And I think all we want to do right now is to limit those surfaces to places where the risk of transmission to people who are at increased risk. And a hospital is a place where people are at increased risk. You're not in a hospital because you're healthy. The same thing is true probably with long-term care facilities. And all of these types of interventions need to be well thought out by people literally following and recording what individuals do. So once you find that out, then you can put the intervention in a particular spot without risking giving us some kind of sterile, non-bacterial environment. And as you probably already know, the microorganisms we carry are very important for us in terms of our digestion and others. There's a huge amount of work now being developed on the human microbiome, all the organisms we have in our different tissues.
Okay. I was wondering then about money, dollar bills. Are we going to, is it a good thing to try and turn them into to have antimicrobial surfaces for paper currency?
Well, there are two things
La
going
dee
on,
dee
I
la
think.
la dee da on the stairs.
I think, Professor Murray, there are two things going on that are, first, yes, it would be good to having some kind of antimicrobial agent put in dollar bills because of the transfer. They carry things from one place to the other. However, I've been seeing more and more articles in the news about us going to an entirely digital society. We're not going to have money anymore. We're just going to wave our cards, our plastic cards. But the plastic cards, of course, if you hand that to an attendant, you're transferring the microorganisms on your hand to their hand. And so if I've been working in my laboratory, chances are when I hand my card to the person at the window at the McDonald's or the window at the Starbucks, they're going to pick up those microorganisms on their fingers. So I think we have to, how are we all going to do these things? Are we going to, just wander around with some kind of magic thing that we can wave and we don't have contact and to transfer things anymore?
Right, right. Yeah. Well, I think very good topic and lots of things to think about, lots of research to be done, lots of new products for the entrepreneurial. This has been a very good presentation, and I really appreciate you accepting our invitation. And maybe we might have you back because there are lots of other remaining things that we could discuss. but like to go ahead and give you a round of applause and thank you very much for your presentation.
Professor Murray, thank you so very much for this invitation. I've enjoyed it. I've gotten new ideas. Your students are clearly much more interactive, and I appreciate that a great deal. And if this is a new way for us to teach, it seems to be a very good way, and I congratulate all of you for participating in this. Thank you very much.
Thank you very much. Bye.
Bye-bye, everybody.